The conductivity and molar conductivity of an electrolyte change with the concentration of the electrolyte. As concentration decreases, conductivity decreases for both strong and weak electrolytes. This is because there are fewer ions per unit volume to carry current as the solution is diluted. However, molar conductivity increases as concentration decreases. The variation is different for strong electrolytes and weak electrolytes. Before we discuss the concentration dependence of molar conductivity, we must first understand the idea of limiting molar conductivity. This is the conductivity of a solution as its electrolyte concentration approaches zero. Limiting molar conductivity is given the symbol lambda m naught. The molar conductivity of strong electrolytes is weakly dependent on concentration. If we plot a graph of molar conductivity against the square root of concentration, we see that the y-intercept is the limiting molar concentration. The slope of the resulting line is the Kohl-Rosch coefficient, which depends on the specific salt. The Kohl-Rosch coefficient depends on the cation and anion charges of the ions formed by the electrolyte. You can classify electrolytes by the charges formed. For example, NaCl is considered to be a 1,1 electrolyte, since the sodium ion is +1 and the chloride ion is -1. Using similar reasoning, you can classify calcium chloride as a 2,1 electrolyte. Magnesium sulfate is a 2,2 electrolyte. All electrolytes of a particular type have the same Kohl-Rosch coefficient. Kohl-Rosch carried out studies on limiting molar conductivity for a variety of electrolytes. From his work, he deduced the law of independent migration of ions, or Kohl-Rosch's law. This law states that limiting molar conductivity can be represented as the sum of the individual contribution of the anions and cations of the electrolyte. For a salt of general form AyBz at infinite dilution, limiting molar conductivity is equal to Y times the limiting molar conductivity of cation A plus Z times the limiting molar conductivity of anion B. Try to work through this problem on your own before checking the answer. Calculate the limiting molar conductivity for sodium sulfate from the data given here. Sodium sulfate contains 2 sodium ions and 1 sulfate ion. From Kohl-Rosch's law, the limiting molar conductivity is equal to 2 times the limiting molar conductivity of sodium ions plus the limiting molar conductivity of the sulfate ions. Substituting the values from the table, we get the limiting molar conductivity of sodium sulfate as 260.2 Siemens, centimeter square per mole. The molar conductivity of a weak electrolyte depends greatly on the concentration of the solution. This is because weak electrolytes have a low degree of dissociation as concentration increases. Since the relationship isn't linear, we can't determine the limiting molar conductivity by extrapolating back to zero concentration. At infinite dilution, the electrolyte dissociates completely, but the conductivity is so low that it can't be measured directly. Instead, we can use Kohl-Rosch's law to find the limiting molar concentration. we can approximate the degree of dissociation, alpha, for a weak electrolyte as the ratio of molar conductivity to limiting molar conductivity. If the molar conductivity and the limiting molar conductivity known, then the dissociation constants for weak electrolytes at a given concentration can be found. Here is a typical problem. The conductivity of a weak acid in solution with a concentration of 0.002034 molar is 5.67 into 10 to the power minus 5 Siemens per centimeter. Calculate its dissociation constant if the limiting molar conductivity is 452 Siemens centimeter square per mole. Try to solve this problem on your own before checking the solution. First, find the molar conductivity using the equation you learned earlier. On substituting the values, we get the molar conductivity as 27.88 Siemens centimeter square per mole. Now, you can find the degree of dissociation for this weak acid, since you know that alpha, the degree of dissociation, is the ratio of molar conductivity and limiting molar conductivity. By substituting the values and simplifying, we get the degree of dissociation as 0.06168. With the value of the degree of dissociation in hand, we can use the equation relating Ka and alpha. Substituting the values, we get Ka is equal to 8.25 into 10 to the power minus 6.